Picture this, you're a scientist, it's 2005. Your spacecraft has been in the void for 7 years, finally orbiting Saturn. You point the cameras at a tiny, ice-covered moon, one that nobody really expected to be interesting, and what you see stops you cold. Geysers, enormous violent plumes of water vapor erupting from the South Pole and blasting hundreds of miles into space. Not on a planet, not on a large moon, on a frozen 500-kilometer-wide rock that by all logic should be completely dead. That moment didn't just change what we knew about this one moon. It changed what we thought we knew about where life could exist in our solar system, and maybe in the universe. This is Enceladus, and its story is far from over. At first glance, Enceladus seems like a footnote. It's Saturn's 6th largest moon, barely the size of the state of Arizona. Orbiting in the outer solar system where the sun is so faint it provides almost no warmth. Surface temperatures sit around minus 330 degrees Fahrenheit. By every measure, this should be a dead, frozen wasteland. But the universe has a habit of humbling our assumptions. What we've discovered hiding beneath that frozen shell, and what we're still learning even now, more than a decade after our best probe was gone, is nothing short of extraordinary. A global liquid ocean, hydrothermal vents, organic chemistry of breathtaking complexity, and the very real possibility that something is alive down there. Today we're going to dig into all of it. The discoveries Cassini made, the breakthroughs that came after its death, and what our next missions might finally confirm. Because Enceladus isn't just interesting. It might be the most important world in the solar system. The story of Enceladus starts with one of history's great astronomers. In 1789, Sir William Herschel, the same man who discovered Uranus, spotted this tiny moon using the most powerful telescope ever built at the time. He and his sister Caroline had spent over a year polishing its half-ton mirror by hand. And even through that instrument, Enceladus looked like nothing, a faint, unremarkable point of light. For nearly 200 years, that was the entire story. Then came Voyager. In 1980 and 1981, Voyager 1 and Voyager 2 swept past Saturn on their grand tour of the outer solar system. Their images of Enceladus didn't show the expected cratered, ancient surface. Instead, they revealed something puzzling. Huge sections of the moon that were smooth, crater-free, and geologically fresh. That kind of terrain only happens one way. Something had reshaped it recently from the inside. Even more intriguing, Enceladus sat right at the center of Saturn's E-ring, the broadest, most diffuse of Saturn's ring system. That ring is made of microscopic ice particles. Something had to be putting them there. Scientists suspected Enceladus was the source. But how? And why? Those questions sat unanswered for 2 decades. They were part of what pushed NASA and ESA to plan a mission back, a mission that would become one of the most productive in the history of planetary science. The Cassini-Huygens spacecraft launched in 1997, executed a gravity-assist slingshot around Venus twice, and finally reached Saturn in 2004. It carried 12 scientific instruments and represented a $3.26 billion bet that the Saturn system had more to teach us. Nobody expected the payoff to come from this particular moon. In early 2005, on its first close flybys of Enceladus, Cassini's cameras caught the impossible: active geysers blasting from a series of long fractures near the South Pole. These structures scientists would come to call the Tiger Stripes. These vents were ejecting roughly 440 pounds of water and ice every single second at speeds exceeding 1,400 miles per hour. The material was shooting straight into space and raining back down on Enceladus, while also feeding Saturn's E-ring directly. Enceladus wasn't dead, it was alive. NASA made a decision that engineers still talk about today. They rerouted Cassini on a maverick trajectory, threading it just 30 miles above the surface to fly directly through the plumes and taste what was in them. What those instruments found would set the next 2 decades of astrobiology on fire. Here's how NASA defines life when searching for it beyond Earth: a self-sustaining chemical system capable of Darwinian evolution. It's deliberately broad because life might look very different out there. But in practical terms, scientists break it down into 4 requirements: liquid water, energy, the right chemicals, and time. Let's go through them one by one, because Enceladus hits every single mark. Water. There's no question Enceladus has liquid water. Cassini confirmed it. The real question was scale. How much water and where exactly was it coming from? Initial data suggested a small, lens-shaped ocean beneath the South Pole. That model got blown up in spectacular fashion when scientists noticed something subtle in the data: Enceladus wobbles. The moon librates, rocks back and forth in its orbit, significantly more than it would if only a small polar ocean existed beneath its surface. The math only worked one way. The ocean had to be global, wrapping around the entire rocky core. Then in 2025, researchers from Oxford, the Southwest Research Institute, and the Planetary Science Institute went back through Cassini's 2005 and 2015 observations of the North Pole. They found unexpected heat, about 7 degrees warmer than models predicted. Both poles are radiating energy. That means Enceladus is generating far more internal heat than previously thought, and the ocean may have been stable for a very long time, potentially billions of years. Energy. This is where things get really interesting. Surface temperatures on Enceladus are more than 300 degrees below 0 Fahrenheit. There's absolutely no way water should be liquid from solar energy alone. The sun barely registers out there. So, where's the heat coming from? 2 sources. First, radioactive decay in the core, but that alone only accounts for about 1% of what Cassini was seeing. The real engine is tidal flexing. Enceladus is gravitationally locked to Saturn, always showing the same face to the planet. Saturn's massive gravity constantly kneads the moon's interior, generating friction and heat deep in the rock and ice. Think of it like bending a paperclip back and forth. Eventually, it gets warm. That heat then has to travel from the core to the ocean above it. How? The leading model involves water seeping down through cracks in the porous silicate core, heating up, and rising in focused hydrothermal plumes along the seafloor, particularly concentrated beneath the South Pole. In 2022, a study led by Wanying Kang used ocean salinity models derived from Cassini data to confirm this. The salinity of Enceladus's ocean, slightly less than Earth's oceans, only makes sense if there had been, or currently are, water-rock reactions happening at depth. In other words, hydrothermal vents, right there on the floor of an ocean hundreds of miles beneath the ice. On Earth, hydrothermal vents are one of the leading candidates for where life first began. They pump heat, minerals, and chemical energy into the water around them, creating rich environments where complex chemistry, and eventually life, can emerge. Finding the same process on a small moon orbiting Saturn is not a small thing. Chemicals. This is where Cassini's mass spectrometer earned its place in history. A mass spectrometer works by ionizing molecules and breaking them apart, then identifying the pieces. It's incredibly sensitive. On its low-altitude plume flybys, Cassini detected hydrogen, a probable fuel source for early microbial life, along with complex organic molecules containing carbon, oxygen, and nitrogen. But the mission ended before scientists could fully process everything. An analysis in 2018 confirmed the presence of ring-shaped organic compounds and simple oxygen-bearing molecules. Then in 2022, the discovery that stunned the community: phosphorus. Its detection in Enceladus's plume material completed the set. Carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. The 6 elements scientists consider essential to life, known by the acronym KNOPS, all present, all accounted for. And then it got even more interesting. A team led by Nozer Khawaja from the Institute of Space Systems in Stuttgart spent years developing new analytical methods for interpreting Cassini's plume data. The problem was that crashing a mass spectrometer into ice particles at 40,000 miles per hour produces a very different spectral fingerprint than a pristine lab sample. It's the difference between slicing a watermelon and throwing it into a blender. The pieces look different, but you can learn to recognize what they came from. Their results, published after more than a decade of work, focused on samples collected when Cassini passed just 12 miles from the surface. These particles that were only minutes old and hadn't yet been altered by solar radiation. These were the closest thing to an untouched sample of Enceladus ocean ever collected. What they found: carbon dioxide, complex carbon-rich alkanes and alkenes, cyclic esters and ethers, ethyl groups, and additional nitrogen and oxygen-bearing compounds. These aren't just chemicals, they're molecular building blocks, the kind of functional groups that, given the right conditions, can drive increasingly complex reactions. In laboratory settings, reactions of this type can eventually demonstrate the first steps of Darwinian evolution. All 6 KNOPS elements, all confirmed, in an ocean beneath an ice shell on a moon of Saturn. Time. The 4th requirement, time, is the one that's hardest to measure. Life doesn't emerge overnight. On Earth, it took hundreds of millions of years. We need to know whether Enceladus has been geologically active long enough for complexity to develop. Cassini's 13 years at Saturn couldn't answer that on its own, but here's where the story takes a turn. Even after Cassini was gone, deliberately sent into Saturn's atmosphere on September 15, 2017, to prevent contaminating Enceladus and Titan with Earth microbes, the science kept coming. The James Webb Space Telescope turned toward Enceladus in 2023. A team led by Dr. Geronimo Villanueva used 10 hours of JWST time to observe the moon. What they saw was staggering. The plume erupting from the South Pole was vastly larger than anything Cassini had documented. It was expanding to a size 20 times larger than the moon itself, a column of water vapor reaching deep into the Saturn system. These observations had 2 major implications. First, they extended the known window of geological activity well beyond the Cassini era, suggesting the venting is long-lived and continuous, not episodic. Second, they solved a mystery that had puzzled scientists for years. Where does Saturn's upper atmosphere get its water? The answer is Enceladus. This small moon pumps water into a massive torus of ice particles surrounding the planet, making it the only known moon in the solar system that actively affects the atmospheric chemistry of its host planet. There was another surprise buried in the data. As ice particles from Enceladus travel through the Saturn system, they lose electrons and become ionized. This creates an electrically charged plasma that interacts with Saturn's magnetic field, generating plasma waves up to 300,000 miles long, structures called Alfvén wings. We don't fully understand them yet, but they're a reminder that even the physics of Enceladus keeps delivering surprises. Meanwhile, researchers Georgina Miles and Carly Howitt went back through Cassini's composite infrared spectrometer data, raw thermal measurements taken over years, and compared them against models of how heat should propagate through the moon. The result? The total thermal output from Enceladus's surface matches, with remarkable precision, the predicted heat generation from tidal flexing in the core. This is significant because it implies a stable, sustained heat source, not a temporary burst, but a self-regulating system. Exactly the kind of long-running environment where life could take hold and persist. And then there's this. In 2017, amateur astronomer Ted Strike was reviewing old Voyager images from the early 1980s when he spotted something that had been missed for 3 decades. A plume, faint but unmistakable. Enceladus may have been venting into space since before many of us were born, and nobody saw it because they weren't looking for it. That realization cuts both ways. It's a reminder that discovery is partly about expectation. We find what we go looking for. And now we know exactly where to look. Cassini's mission ended. JWST has given us a new window. But what we really need is boots, or probes, on the ground. Or rather, in the ice. Several missions are in various stages of planning. The European Space Agency has a mission targeting launch in 2042, with a planned arrival at Saturn in 2053 and a potential landing on Enceladus in 2058. That's a long wait, but what it would do, make direct contact with the surface and sample material near the Tiger stripes, would be unprecedented. ESA's JUICE mission, the Jupiter Icy Moons Explorer, is already en route and expected to reach Jupiter in 2031. While not focused on Enceladus specifically, its mission to investigate the emergence of habitable worlds around gas giants will generate data and methods directly relevant to understanding moons like Enceladus. NASA's Dragonfly mission to Titan, launching later this decade, will deploy a nuclear-powered rotorcraft drone, the first ever on another world's natural satellite. Titan is in many ways the chemical prequel to what might be happening on Enceladus, and its results will sharpen our models significantly. And then there's the mission that gets scientists genuinely giddy, the Enceladus Explorer, funded by the German Aerospace Center. It proposes sending a nuclear-powered device called an ice mole, which does exactly what the name implies, to drill or melt its way through the ice crust. And into niches within the ice where liquid water might be accessible without ever descending all the way to the ocean. These niches could be where any subsurface biology first encounters the surface. They'd be protected, stable, and potentially rich with evidence. If any of these missions find even indirect evidence of biological processes, it won't just be a discovery about Enceladus. It will be a discovery about life itself, about how common it is, and how many places in the galaxy it might call home. There's a quote from physicist Jeremy England that I keep coming back to. You start with a random clump of atoms, and if you shine a light on it for long enough, it should not be so surprising that you get a plant. England's point is that life might not be the astronomical long shot we've assumed. Given energy, time, and the right chemistry, complexity has a way of emerging. It might be almost inevitable. If that's true, and the evidence from Enceladus increasingly suggests it could be, then the universe is not empty. It's teeming. And we've been looking at one of our best leads for decades without fully realizing what we had. Enceladus is 500 kilometers wide, a frozen moon around a gas giant, hundreds of millions of miles from Earth. And beneath its ice right now, there may be an ocean older than our civilization. Heated by the gravitational pull of the largest planet in the solar system, laced with the chemistry of life and waiting. We put one probe there, we're still unpacking what it found. And what we're finding keeps getting more remarkable. Imagine what we'll discover when we go back.